Let me introduce Mr. John Thornton. It's our pleasure to invite him being here, giving us this technical session about Bruker AFMs. I am the research associate at NUFAB Cleanroom, and here in the panel we have Dr. Gajendra from SPID. Both of our centers have a few AFM for offering the research as a research tools to the users. From my side, NUFAB Cleanroom has been recently expanded. We have a couple new tools, the thin film tools like ALD, and also a few thin film deposition tools. We also have the new E-beam writer is coming. At the same time, we have a few dry etching and wet etching tools to help the users conveniently check their pattern and have the requirement of contamination free. We acquired a small version of Bruker Icon inside the clean room. Dr. Gajendra, he has a few more advanced versions of Bruker AFM. This new AFM in our center, it has 3 operational modes. The conventional contact mode and the tapping mode. There is a third one called PeakForce Tapping mode, which is very useful new tool. Today we have John here, and mostly he will talk about the difference between the other conventional modes and how it is useful. Hi, Gajendra, do you have anything to talk about your side? Hi. Oh, he is. Oh, he's off. Hi, Katie. Then can I handle everything to John? John, would you like to start with all the technical side of the AFM?
Sure. Yeah, absolutely. Thank you very much, Xiaoning, and thank you everybody for inviting me. My name is John Thornton. I am an applications engineer with Bruker. I specialize in AFM, and I've been working with AFMs for a long time, and I really enjoy AFMs quite a bit. So hopefully you guys are using AFMs or are interested in learning about them, and hopefully I can provide some useful information for you. So I am going to go through this presentation. The outline is we'll talk a little bit about the AFMs that you have access to there. You have some very nice AFMs at your university that you have access through the different centers there. And we'll talk about the basics of AFM. So we'll talk about contact mode and tapping. These are very common modes that people use and have been using for many years. PeakForce mode is more recent development, not super recent. It's been around for quite a few years as well, but a lot of people are not as familiar with it. So we'll talk about that. There's some really nice benefits to it. And hopefully I'll get that across to you. We'll talk a little bit about the some advanced modes, not too much about advanced modes. I'll just mention a few things. The instruments can be automated if you want to. I'll throw some application examples in. And I'll give you a few operational and probe tips, so to speak. So some of this is useful for people that are beginning, and hopefully there's a few tidbits for people that are more advanced and operators in here as well. Generally what I like to do is I'm actually going to turn off my video, if that's okay, just for bandwidth, and just keep with the presentation, but I'm still here, I promise. So we'll just continue here. So these are the AFMs that you have, that I'm aware of anyway, at your centers. You have the Dimension Edge, which I understand is in the clean room. You have a couple Dimension icons. One is a FastScan AFM. And I believe you have the Resolve. The Resolve, I'm not really going to talk about. The Resolve is really designed for biological AFM to work with optical microscopy techniques like fluorescence, confocal, really nice AFM. But that's really not as, these modes I'm going to describe will apply to that instrument as well, but I won't get into that one so much, really concentrate on the dimension AFMs. Okay. So let's talk about some of the basics of AFM. If you're new to AFM or just kind of getting started with it, of course, it's important to understand how the modes work, how the instrument works. When you're interpreting how to run it and interpreting the data that you get out of the tool, it's important to know how it's collecting the data. So this is a very generic image of an AFM, where basically you have a feedback loop, which is trying to maintain a constant tip sample. So this usually is with respect to force, and you can be looking at deflection or an oscillation, depending on the mode, which we'll talk about. The laser bounces off the tip into a split photo detector, and you're trying to feedback and keep a constant signal with the controller. That goes, and at every data point, it'll move the scanner in Z in order to create your, to adjust the height of the sample. In this case, this is a sample scanning AFM. In order to keep that tip sample interaction constant. So the image comes from Z. It doesn't come from the cantilever, but it comes from the Z motion of the scanner. And then the XY is creating the raster to do the raster area scan. So it's a rastering instrument. You know, resolution can get down to atomic resolution. Usually people are doing a few nanometers is more typical. Common applications, most people are doing topography. And I'm going to talk a lot about topography because I understand that's a lot of what people are doing that are in our audience. But there's a lot of other things you can do too. And you have really nice AFMs that have many different options on the different tools to look at mechanical or electrical modes. I'll mention those, but I won't get into that too much. And this works in ambient and fluid environments. I'm going to mainly concentrate on ambient, but it works in fluid for biological, electrochemical applications, things like that. An important part of the AFM, of course, is the probe or the tip. A lot of times when we talk about the probe, we're talking about the cantilever, the substrate or the chip, and the tip itself. And there's, you know, when you start talking about the different modes, we use different tips depending on the mode you're using, because it'll have a different interaction and a different mechanism for imaging. You can see the size of a human hair here, and you can see the size of the cantilever. So they're quite small. Some of these are V-shaped cantilevers, and some are single beam, and some have these funny shapes to them. And then the tips themselves can have radiuses down to a nanometer in some cases. And some of them are intentionally dull. Some of them have high aspect ratios. So sometimes depending on what you're trying to do, type of sample or type of measurement you're trying to make, you would choose a different tip. We do make tips as a company. So we design a lot of new modes. And so we make tips, try to optimize those modes, you know, so people get the most out of the instrument development. So there's a lot of information at this website, and I'll have some links in this PDF. I can, not PDF, but the PowerPoint, which I can send out as well. And so I'll mention some of the tips for the different modes, like in this slide. So this is contact mode. Contact mode has been around a long time. It's a relatively easy mode to run. It's one of the first, it's really the first commercial mode in the late 80s. So it's been around a long time. And the idea is quite simple, really. The cantilever is in contact with the sample the entire time, and it drags across the surface. So it's basically you have a laser, or the light is bouncing off the back of our cantilever going into a split photodiode. When it goes over a bump, the cantilever deflection changes. That changes the reading out of these two detectors, and the scanner is adjusted in Z in order to get the original reading back. So at every data point, there's some change in Z in order to keep that deflection, which keeps your force constant. So that's contact mode. Common cantilevers for this have pretty low spring constants. They're usually, like I said, these V-shaped cantilevers, but not all of them. These are common model numbers, and there's a web link here if you're interested in digging into it more. But they're usually low spring constant, very soft cantilevers, so they don't apply very much force. So contact mode has good and bad, just like everything. It's nice on hard samples. So on a sample like this metal film, it's 10 microns. I'm not doing super high resolution. It works quite well. This is a large scan on a hard sample. This is silicon, a solar cell example where you have these pillars here, these triangles, pyramids. And it's a large scan. This is actually a little larger than the dimension does. The dimension does about 90 microns in XY and about 10 microns in Z. So this is a little larger area scan than on a typical dimension. But the idea is the same. It's a large area. It's really rough. These things are several microns tall, the features, so there's a lot of roughness here. Contact mode is really nice versus the other modes for this application. The feedback is a little faster than tapping or PeakForce, and so you can scan a little faster, and it'll do a better job on the really rough hard samples. It does a great job. So a lot of applications are simply you get the data. Once you have it, there's quite a lot you can do with it. These are some pretty simple cross section looking at the angles that they were interested in, which was 52 degrees. And as long as you have a tip which has steeper sidewalls than what you're trying to measure, then you get an accurate measurement. Okay. The downside of contact mode, and one thing I'll advise you is if you can avoid contact mode, unless you have that very specific applications, I tend to advise avoiding contact mode because it does tend to apply a lot of force on your samples. So that'll reduce your resolution. It may damage your samples. It may wear your tip out very quickly or dull your tip. This is a really old example, but I still like it because it really gets the point across in that this is an epitaxial silicon layer. These are atomic steps in the silicon. These are epitaxial steps. So 1 micron image on the left, when you zoom out, you can see that you actually created a pit. So the dark area is lower if you're not familiar with the AFM as much. So just by imaging in a contact mode, you've actually destroyed it. So contact mode can be a destructive mode in some cases. So you need to be careful with it when you get into softer materials, is that it could start changing things. Some modes require it, some conductive AFM, some of the modes require contact mode in certain instances, and then you just have to do your best with it. But that was a big motivation for developing other modes. So tapping mode came along later in the early 90s. The idea behind tapping is that we oscillate the cantilever instead of staying in contact the whole time at its natural resonant frequency. And then we tap on the surface at that frequency. So we have a little piezo, which is oscillating the tip in the tip holder. And we have a free air oscillation, and then we bring the tip down until it's close to the surface. Until it starts tapping on it. The amplitude is reduced because the sample's in the way now, and the feedback loop just keeps that constant. So the tip is approaching, contacting the sample, then pulling all the way off. So in order to do that, you need cantilevers which are quite stiff. If you use a soft cantilever to do this, it'll just get stuck on the sample and it won't work very well. So common tips for this usually are tips that have resonances around 300 kilohertz, which is relatively high. That's 300,000 taps a second, and 40 newtons per meter spring constant, opposed to contact and peak force, which we'll get to next, which is around 1 or less. So 300 versus less than 1. So it's a big difference in 40 newtons per meter versus less than 1 newton per meter in the other mode. So it's quite a bit stiffer cantilever. But it became very popular. So a lot of people doing AFM in the world are doing tapping. And the benefit over contact mode is that it really controls the forces a lot better. You're not dragging the tip, so the lateral forces are better. It's not stuck on the surface, so the vertical forces are better. It just allows us to get higher resolution data. So, so a lot of people are doing tapping, and that's fine. We actually were developed that many years ago. So same example, again, the old example, but it still rings true. You know, same sample, you just zoom out and you don't see the change. So that's the benefit. We used to do a lot of work on, and I guess we still do in certain industries, a lot of work on polysilicon films. Polysilicon films will wear a tip out before you get to the end of a scan. You just watch it dull as you scan down to the bottom, and you're like, wow, start over. So tapping really helped with that. Contact mode, the tips were just eaten immediately. In some cases, we even used some coatings on the tips to make them more robust for this application. And there are there's a technique called phase imaging with tapping where you can look at mechanical properties. And so it's a really easy technique in that you can bring up the phase image and you look at the lag in the oscillating signal between the driving signal on the tip that makes it oscillate up and down versus the response. And if you get a lag in the response, if it's slower or faster than the differences anyway, if it's a difference than the driving signal, then that can be due to differences in stiffness, differences in adhesion. Energy dissipation is a big part of this, viscoelasticity. All those material properties can create this phase lag in the signal. And so you end up getting an image of height. This is our height and this is our phase. So I can see I have two different phases of the material. And this is nice because I can't see it in the height, but the only downside to this mode, or a major downside, is I don't really know what's causing that contrast. Is this a difference in stiffness? Is it adhesion? Is it a combination of the two? It's impossible to really tear them apart. And there's a lot of papers on people trying to do that. There's different ways to approach that, but it's very complicated. So one way around this is basically to do something called a force curve. And so force curves have been around AFM for a long time as well. Traditionally, they are not imaging modes. And the idea is that you can approach the tip to the sample and look at the tip contacting and pulling off the surface. And so you end up with a curve like this where you have a distance of the tip approaching, contacting the sample, and then we have deflection here. So in orange, the tip approaches, it jumps to the surface, it's in contact the entire way, it deflects upward. And then it comes down here, and then it takes a little more force to pull off the surface. Could be due to absorbed water vapor, adhesion, a number of different things. And then it pulls free again. So that's a force curve, and I can measure a lot of things with this. I can measure differences in stiffness. I can measure, looking at the contact part of the curve, stiffer materials will have a different slope. And then we can fit models to it, like a Hertzian mechanics or Snedden or other ones, in order to get, a modulus value. I can also measure my adhesion. So I can look at how much force it takes to pull the tip off the surface. And there's other things I can measure as well. Long range attraction, energy dissipation. There's a bunch of things you can measure from a force curve. So we can make an imaging mode out of this, and that's what PeakForce tapping is. So PeakForce tapping really was developed in order to get quantitative mechanical information out of an AFM. So we can get the phase channel, but it's not quantitative, and it can be really flaky, and I'm not really going into all of that. It's useful, it's quite useful, but it's just difficult to quantify. So back about 10 years ago, we teamed up with Dow in order to get quantitative information out of this. So the idea is it does a force curve, it does it very quickly, usually at 2,000 force curves per second, so 2 kilohertz, and it will create a force curve like this. It'll also plot it versus time. So this is approach, deflection, adhesion, and coming off again. And so we did this for mechanical properties, but what we figured out is that there's a lot of great topography imaging benefits to it also. And I'll mainly talk about that actually more than the mechanical properties, although we'll talk about how that works also. But the idea now is that I'm usually tapping at 1 or 2 kilohertz. And if you remember, I was saying tapping mode usually taps at 300. So this is way below resonance on purpose. We feed back on the cantilever deflection. We can have extremely low forces. We can get down to 50 or even less as far as the amount of force that we're applying, which is quite low. And the scan rates are typical, similar as tapping mode. So 5 to 10 minutes an image. There's a lot of benefits to this as an operator. One is that I can see the force curves live the entire time, and this is true on the edge or on the icon. And so as you're scanning, I can look at that tip sample interaction, and I can tell if I'm having a problem much easier than I can in contact or tapping, because I have this force curve that I'm looking at. And so I can look at this force curve and I can tell I'm on an area which is softer because the tip contacts, it has a shallow slope, a little bit of hysteresis here, a little larger adhesion. Whoops, sorry. There, and then we have an area that's harder, much less adhesion, much stiffer slope. And I have a nice curve. The tip is approaching, deflecting up, there's a little adhesion, and it comes back again. And so the way it works is I tell it how much force I want. In this case, whoever did this was doing this at 10 nanonewtons, and it feeds back on that. So I can type 10 nanonewtons into my feedback if I have a spring constant that's calibrated. So this is a nice mode for a number of reasons. One is just from the operator point of view, it's nice to be able to look at what's going on and tell if you're not getting a good image and you look at your force curve and you have this humongous adhesion, maybe the tip's getting dirty or dull. There's different tips that we use for these. Some of them are V-shaped, some of them are these little kind of almost paddle-shaped, the narrow base and a wide end to it. And with the tip, these are combinations of a silicon tip and silicon nitride cantilever. So these ScanAsyst Air, ScanAsyst HPI is this paddle-shaped one, are very nice probes for this mode. You can also use contact probes, but generally they're low spring constant probes, like less than 1 Newton per meter for this mode. Another nice benefit of this mode is that we can automate it. So both have what we call ScanAsyst, which basically will adjust your feedback parameters for you. This is really nice for people that are new to AFM. It's nice for people that just want to use it every now and then. They don't want to be AFM gurus. They just want to get their data and go on their way, which is fine. And also for people that have been doing it forever, like me, it's nice as well. You have 3 main imaging parameters: your set point, which is your force; your gain, which is how fast the feedback responds. It can give you a good image with a good gain setting. It can give you a noisy image with a bad gain setting. And also the scan rate. It'll adjust these 3. In tapping and contact, you would adjust these manually. It's also adaptive. So as you're scanning along, if you hit some big bump, then it'll adjust these parameters during the scan. So it's not preset, so that's nice. And, you know, if I didn't make this clear earlier, we don't tune the cantilever in this mode. There's no resonant frequency tune in this mode, which is a nice thing. I like not having resonance. And you can turn this off if you want. These are auto controls. I can turn this off and adjust everything manually. So, you know, it's a nice mode to have as a complement to the other ones. It does a very nice job on trenches, and I'll actually show you a better example of that in a minute. But it does a better job than tapping on high aspect ratio structures. I was doing a lot of work on these fibrous polymers, PTFE and some different things. It does a great job on that. Tapping has a real problem with it. It tends to change the oscillation in tapping and becomes unstable. So it's, you know, it's nice to be able to go back and forth between the different modes depending on what your challenges are. And it's a high res mode. And in fact, all of these modes are high resolution modes. The nice thing about PeakForce is you can control the force so much better so that you can really fine tune how much force you're applying, because that affects the resolution you're going to get. That's the main drawback with contact, is you can't control the force very well. It's usually high. In this mode, I can see my force curve, and I can even adjust it so the cantilever is not even deflecting up to the free air point. I won't go into all that, but anyways, you have a lot of control over how much force you're applying. So that allows you to get really nice data out of it. And this is true for both instruments. So the advantages, this is just kind of a nice little high-res image of a polymer. You can see the chains, molecular chains here. The advantages are, you know how much force you're applying, and you can keep the forces low. Avoiding contact mode is a good thing. And I like to be able not to have to worry about the resonant frequency of the tip, how well the tip's sitting in the holder and all that jazz. It's nice to just not worry about that. It'll automatically adjust your parameters if you like. It's a little easier to learn, and we can get quantitative mechanical properties out of this if you're interested in that. And it's, you know, it's a mode that's grown a lot. We get about 1 or 2 publications a day that are peer-reviewed out of this mode now. So it's a really well accepted mode at this point. And there's a lot of versions of it which give you other things like mechanical properties, electrical properties. And it's a growing area. So you'll see a lot more out of this mode. I'm mainly concentrating on topography, but there's a lot more we can do with it. And I'll briefly mention some of As far as topography goes, common applications, like I said, most people in the world with AFM are doing topography measurements. So people are measuring heights and depths, and angles, widths, roughness, just looking at morphology. And it's a nice complement to other techniques, such as electron microscopy or optical techniques. This is a really common application. It's just indium gallium nitride film, which was created by two different processes. And on one process, you get a lot of defects. You have a roughness of 5 nanometers RMS. With another process, those defects are gone. You see a few screw dislocations. You see atomic steps and order of magnitude lower RMS. This is probably one of the most common uses of AFM. This is an old application article, actually, that we use tapping mode on this. So this is very common. This is PeakForce data. This is another common application, just super smooth structures. This is silicon. It has RMS of 1.8 angstroms and an RA of 1.4 angstroms. This was a repeatability study just showing that the tip doesn't change or dull with it over 21 images in this case. This was done on the Icon, but could also be done on the edge just as well. Or step heights. So the instruments have a noise floor of a ½ angstrom on the edge, 1/3 of an angstrom on the Icon. So they're essentially, they can do atomic resolution in Z, even if they're not seeing atoms laterally. And so this is kind of a nice example of really high resolution in Z, where we have basically a single step of graphene. This is a 300 picometer step. So very small structures like this, and very tall structures, which I'll show you, I think, in just a second. This actually I did in grad school. So I was doing AFM a long time ago, and the colleague of mine was doing scanning electron microscopy, and he couldn't tell if this film that he had grown had pits in it or bumps, just because you're getting secondary electrons off edges. You couldn't tell if it was a pit or a bump, because it could be either one. And so we threw it in the AFM, and it just popped right out. There are bumps. So it's a nice complement between the two techniques. And of course, it can go the other way as well. The SEM and the AFM are nice complements to each other. These are trenches. There's a lot of trench metrology done with AFM. A lot of times, if you're doing that, you'll be using a high aspect ratio tip, like the one, there's many different types. There's one in the upper corner there. And we can measure up to about a 10:1 aspect ratio. This example shows the cross-section is about 2 microns deep, about 500 nanometers wide, so about 4:1 in this case. This also would complement well with SEM, and of course you don't have to cleave it in this case. One thing that we found was that if you're doing high aspect ratio structures, PeakForce mode tends to work better. In fact, when we originally came out with this mode, we called it NanoTrench, and we used it for this application in some of our automated tools. And really the reason is in tapping, you have a lot of trapped air in your trenches. So when the tip goes down into the trench, the amplitude goes down because of the trapped air, not because it reached the bottom of the trench. So you have to be really careful that you're reaching the bottom of the trench if you're doing it in tapping. And people do it in tapping. They've been doing it all, for years. But we find it is much more consistent, much easier to do in PeakForce mode. So this is the same sample, and you can see the difference in the cross sections there. So we do a lot of work with PeakForce mode and with high aspect ratio structures, and a lot of times these high aspect ratio tips. And this is just one more example, something similar, high aspect ratio structures. This is comparing with the SEM, where when they cleaved it, the sample changed, and the depths were abnormally shallow. So nothing against SEM. I like SEM a lot, but it's a nice complement to other techniques. And I could show you some optical things as well, but we'll keep moving. So I have a section here on similarities and differences between the two instruments. These are both great instruments. Even if you're just doing topography, they're both quite nice, and they can do a lot of different things. The Icon can do more. It's kind of where we do a lot of development, and you have a lot of options at Northwestern on the icons you have there, which is great. I mean, you really have a nice set of capabilities that you have access to, which is really nice. One thing about the two instruments, they're both stage instruments, they're both tip scanning instruments. So the samples are held down by vacuum, usually, or maybe magnetically, depending on what you're trying to do. But I usually try to use the vacuum stage just to hold the samples down. And then you can see the stages are 6-inch and 8-inch diameter. One thing about them is they both use the same scanner. So if you've used one, you'll be familiar with the scanner on the other one because it's the same one. It's the same scanner. It's a closed loop scanner. It has 90 micron XY range, 10 micron Z range. Closed loop means it has sensors monitoring the scan and correcting it, any inaccuracies as it scans. So it's very, very accurate, and it's very stable. It's a really nice, both of these are very nice instruments. Some of the differences, so kind of what I'm going to do here is just kind of jump back and forth between the edge and the icon. So I hope you can, it's easy to follow instead of putting everything all in one section. They have two different controllers. They're a different development pathway, even though they use the same scanner. The controllers came out of different histories, and so does the software. So did the software. So the Icon has the NanoScope 5 controller, which is the 5th in a line of NanoScope controllers. It's a nice advanced controller. You have BNCs on the front where you can access signals if you want to get into advanced work. The NanoDrive controller is what we use on the edge. It also has BNCs. These are on the back, though, that you can access if you needed to apply voltages or something. And the software is different. So this is the edge software. It could be 2 screens or a single screen. I don't remember what you have in your clean room there. But basically you have your main imaging parameters in these 2 locations, and you can bring up the different channels here. And you have your optics and your stage motion. And then the Icon, of course, has your kind of standard choosing different modes and your parameters, and you can choose up to 8 channels. The Edge can choose up to 16. Actually, it has more channels. And then the offline side of things, which we'll talk about briefly. Both these instruments, you can, when you go into them, you'll have a experiment selector where you can choose the modes you want to run. So contact tapping, ScanAsyst is the same as PeakForce mode. And then there's a bunch of different electrical and mechanical modes and some other just kind of things that don't fit into any of those categories. So these are saved workspaces, either from the factory or you can create your own and save one. These are the different modes. In fact, thinking about this, I actually need to edit this, but it kind of gives you an idea. There's actually quite a few modes on these instruments that are standard. So contact, tapping, and PeakForce we've talked about, but you can get into things like phase imaging I talked about. This is for the edge. Magnetic force, some electric force. Nanolithography I actually don't think is standard. I'm sorry about that. And adhesion, which I'll talk about. And then there's a bunch of optional modes here that can be added to the instrument. And then the Icon has similar setup. A lot of the standard modes like phase, magnetic, electric force are there. And then there's a lot of different things you can add on. And you guys have a number of these actually. So I want to talk about PeakForce as more of the emphasis here. This on the edge, this is what the PeakForce screen looks like. So the idea really is you have the ScanAsyst here where we can tell it to adjust the gain or adjust the set point and the gain, either one or the other. So it has the gain adjusted, so all my gains are grayed out, but I'm adjusting my own force, my own set point here. It also has a button for the ScanAsyst setup. So if you click this button, it'll open up a menu where you can tell it how large of a force curve to create, what frequency, and it gets into a couple other things that I'll mention in more detail. We can bring up the force monitor window. On the edge, it looks like this. So now I can see what my force curve looks like while I'm scanning, see if there's any problems or if this looks stable when I'm scanning. So I like to bring this up if I'm doing this mode. A couple operational tips, so to speak. When you're engaging on these instruments, you have control of how much force you're applying. On the Icon, it's actually in a window under Microscope engage settings. And you're basically telling it how much cantilever deflection to look at on the detector. So this is a pretty standard setting. This is 150 millivolts on the detector. I like to have it usually above 0.05 or 50 millivolts to, excuse me, to be stable. On the edge, sometimes this will be set to 0. You don't want it set to 0 because it just won't deflect. It'll false engage. So you usually want to have this around 0.5 if you're doing this on the edge. I usually don't set it real high to like several volts. It'll drop it back down automatically if you do that. So 0.5 is a good thing to have. If you forget, sometimes you may false engage and have some trouble. So you don't want to do that. Also, a couple other parameters I notice a lot of people aren't aware of when it comes to PeakForce mode on both instruments. One is this button called Autoconfig. So on the edge, it's in that menu I showed you a second ago. This is the force monitor on the Icon. Both of them have an Autoconfig button. And it'll adjust the shape. It'll do a background subtraction, adjust some of the timing of the force curve. So if your force curve looks funny, maybe it has curvature or it's not contacting the sample properly, you can hit the Autoconfig button. You can do it as many times as you want to. There's really not a downside to it. Generally, you just have to do it a couple times and it should fix things if it's starting to act funny. But sometimes it can get out of sync, so to speak. And there's some other advanced parameters you can get into, but most of the time this works. So I wanted to make you aware of that. The other thing is this ScanAsyst noise threshold. This parameter is important if you're doing really super smooth surfaces like that, like the 1.8 angstrom silicon roughness that I showed you a second ago. This controls how the gain is set. So the gain can make things noisy if it's set too high. So it will basically be adjusted so that you have a background noise of whatever this value is. So if you have a background noise, in this case, of 0.1 nanometer or 1 angstrom, the gain will be lower. And that's fine on a smooth surface. You don't really need that much gain to follow the surface. If you have it set to 1 nanometer and you're measuring a 1 angstrom roughness surface, it'll look noisy. So you would want to come in and adjust that down. Or if you had a really rough sample with 2 microns of roughness, you'd probably want to crease that up a little bit. You're not going to notice a little noise in the background. You're measuring 2 micron heights. So a lot of people don't know about that parameter. So I wanted to make you guys aware of that. This is a 5,000 by 5,000 pixel image. This is something you can do on the Icon. The edge will scan up to 1,000 by 1,000 pixels. That's the maximum on the edge. It'll take longer to do these scans, but you end up with a lot of data, and you can zoom up on these later. So these are 300 nanometer zooms. This is glass, like what you would use in your iPhone or your Samsung phone or whatever phone you like. And you can see this particular tip here. This guy has a tip radius of a nanometer. So it's a ScanAsyst HPI-SS for super sharp. It's a nice tip. 1 nanometer typical, 2 nanometers maximum. So that allows you to do images like this. So it's a 300 nanometer scan. You can see a lot of data in these scans. Normally 300 nanometer scans look kind of blurry. But if you can control the force well, which we did in PeakForce, and we have a sharp tip and we keep it sharp, then you can do some really cool stuff. So that's what was done on this example here. Another thing about PeakForce mode, if you're on the edge, you can also collect a channel called adhesion. And that's just standard. That's not an option. So we can get our height image. So if we have a sample like this, we have our height image here, but we can also create a map of adhesion. You have to go in and choose it, but just like you would, deflection or phase or any of the other channels you would normally choose. But this can be a really useful channel. For one, I mean, it can be useful for studies. You can look at differences in distribution of materials. I think this was a time-dependent dynamics study where you can see the adhesion changing as the sample changed. But it can also be a great way to look at tip sharpness and tell if your tip is dulling while you're scanning or getting dirty, because your adhesion will change if it does. So a lot of times I pull that channel up and turn it on just because I want to see if my adhesion is growing as I scan, because if it is, then my tip's getting dull or dirty. So my tip is changing, let's put it that way. For instance, if you have a nice sharp tip, if you're in air, you have absorbed water vapor on anything. And so the tip goes through that, it contacts the surface, it comes back out again. If you have a sharp tip, there's not much water vapor holding that tip down, so the adhesion is very small. If you have a dull tip, then there's a lot of contact area with this water vapor, and there's a large adhesion. So this could be an indicator that your tip is wearing. So a lot of times people doing high resolution work with PeakForce mode will monitor that adhesion channel. This is an example of basically imaging in PeakForce mode, and then they intentionally dulled the tip by increasing the force too high. And you can see how the adhesion would grow as the tip was dulling. So this can be useful if you're doing this sort of work. And this is, again, a topography application, but we're using the adhesion to monitor the quality of your topography. And then there's PeakForce Q&M. This is a mode on the icon. It is not on the edge. In fact, I probably should have labeled the slide that. But it basically takes that force curve and does an analysis like we described and gets images out of it. So I can do a fit to my curve when it's in contact, plays it into a model. We typically use the DMT model for imaging, but you could change it later, or Sneddon, you could use Sneddon. But you could use JKR, you could use several different models we could change it to. But anyway, what it does is it does a fit, and it puts it into the model, calculates what your modulus value is. We can also measure adhesion by how far it pulls downward when it breaks free from the surface, from the free air deflection. Energy dissipation is the area here in between the two curves. And look at the deformation, the indentation, and create maps of all of this. The calibrated range for modulus, we can go down to about 20 kilopascals. That's nice for hydrogels, and if you're doing that, I can give you some pointers if you want to contact me later. Can go up to stiff materials, about 100 gigapascals. And so what you end up getting is you get all this data at one time. So just like I showed you with the edge, you get your height data, you get your adhesion data, and I can see distribution of two materials just on adhesion. I got a polyethylene and a polystyrene. So high adhesion with polyethylene. But I can also get images of modulus deformation. So all this comes out in one scan. It's a very rich data set. There's a lot of data there that you can get modulus deformation and dissipation along with adhesion, and now indentation. That's a newer channel. And if we want to, we can calibrate the spring constant, tip radius. We do have tips that are pre-calibrated for all that. And you can get values of pascals if you wanted a calibrated modulus value. That's really all I'm going to talk about with this mode. If you have questions, I welcome them. Last thing I'm really going to, well, not quite the last thing, but soon, I'm going to go ahead and wrap up here, is that the machines can be automated. So if you want to set it up so that you want to image several different samples, or maybe you have a wafer, you want to image several different areas, you can automate that so that the machine will go and collect the data ahead of time. That's called program move. It's on both instruments. These are standard, it's a standard technique or feature on the instrument, where basically you've told it what XY location you want in Z with the focus, and it'll go to those locations, collect the data automatically for you, and then withdraw, move to the next location automatically, engage. So if you have lots of data that you're going through, that you're collecting on a sample or multiple samples, then this can be useful. So this was an example of basically a screening study. This is a pharmaceutical example. They were looking at films, looking at roughness. This was done with the fast scanning head on the Icon. They did 12 samples, 60 sites in 60 minutes. So that's 1 minute per sample, which is pretty good for an AFM, which is usually 5 to 10 minutes per image. We can go quite fast with the fast scanner. And I'll show you an example of that quickly. The analysis for both instruments is the same. So the software is the same. It's called NanoScope analysis. It's free. I'm sure that you guys have copies there. If I'm happy to give you one if you need one. It works on Windows 10, 7, and XP if you still have an XP computer. But it's free. We just hand it out to anybody. And you can do automation with the images also. I can set up something. In this case, they did a plane fit, and they're doing roughness measurements on all these different scans. And when you do that, you can output that as an Excel file, and this gives you your data, standard deviation, average, things like that. And there's a lot of other things that we can talk about. I'm running out of time, so I'm going to wrap this up. But there's a lot of other modes out there. Your instruments can both do magnetic force microscopy, where you have topography and then your magnetic image. You have electric force microscopy, where you're looking at electrostatic attraction and repulsion, so electrostatic fields. In this case, the sample was biased. You could also bias the tip and look at conductive areas on a grounded sample. Conductive AFM, where you basically measure current. I could do an IV curve. I can make a map like this, where we have a conductive polymer. And I can see I have high current on these molecular strands here that are going to a carbon nanotube, which actually has a little lower current in this case. And there's different versions of this. There are contact mode versions. We try to do this in PeakForce if we can get away with it, just because contact mode would have destroyed this sample. There's multiple versions of this technique. It's called surface potential or Kelvin probe force microscopy, and it measures work function of materials. So it's a somewhat of a quantitative measurement. It'll measure the difference in work function between your tip material and your sample. So this is graphene, and you can see a high work function over a single layer. I showed you this example earlier with the step height, and then a lower work function with multiple layers in this case. Lastly, you guys have a FastScan. FastScan is a beautiful instrument. If you start using it, you'll get spoiled by how fast it runs. This is an example we show a lot, but it's a nice example. It's a polymer which is crystallizing in real time. Each image is 2.5 seconds, and they just created a movie. So scanning at 100 lines per second. Most time with AFM, you're scanning 1 or 2 lines per second. So this is super fast. It can even go faster than this if we want to. But it allows us to look at dynamics, or if you're collecting a lot of data or doing big surveys and having to zoom in. It's a really nice instrument that you guys have access to. So this is my very short summary. Hopefully I gave you a good idea of the instruments. You guys have great instruments there. You do a lot with them. And hopefully I gave you a nice taste for PeakForce mode. I have nothing against tapping. Contact mode I don't like as much, probably tell. But it has some nice things about it which you don't find in the other modes. And it's easy to use, so if you're new to AFM, it's a nice mode to start on because it'll adjust things for you. Control the force well, you can get into more advanced modes with it, as well as tapping, you can get into more advanced modes. And that's my email if you guys have questions. Of course, you have a lot of AFM expertise right there on campus, but anybody's welcome to contact me if I can be of any help. So that's my email. So that's what I have today. So thank you for listening to me.
GS, did you want to finish it up? And then we'll take through the questions.
He is awake.
Okay, John, seems like there's a question in the chat. Do you or Shining want to take that?
I'm happy to answer anything, or try to anyway.
Can you see the Q&A?
Okay, sorry. You want me to look at the chat? I'm sorry.
That's okay. And if you want to share, stop sharing that, and maybe the chat will pop up and people can see. If not, that's fine. You can.
I'm having trouble finding it. Can you just? It short? Can you read it?
Sure.
I'm sorry.
That's okay. For the first question, for KPFM, I got several, and nanomilli particles, can I clearly measure its surface potential? And what is the spatial and current resolution for conductive AFM?
Okay, so you have nanometer sized particles and you want to measure
Surface potential.
surface potential. Okay, so yeah, you can measure, it depends on the size of the particles. Generally with that mode, there's different ways to approach it. Most of the electrical modes use tips that have a coating on them. So you take a tip which is 5 nanometer radius and you coat it with a metal to make it conductive. So now you have a tip which is 25 nanometer radius. So in that case, your resolution is going to be 25 nanometers. So depending on what your particles are, you may still be able to see them, but if they're 5 nanometers, you may not measure that they're really 5 nanometers. They may be artificially enlarged. And you would need a good signal. So those are quite small, so it might be a little challenging, but tubes. So we do have some tips which I believe you guys may have on the Icon, a mode called PeakForce KPFM. It's not on the edge. The edge would use the coated tips. The PeakForce KPFM uses tips that have a tip radius of 2 to 5 nanometers. So we have resolved 2 nanometer wide single carbon nanotubes with KPFM. Now, if it is correct or not, I don't know. But you can certainly resolve that. For EFM, same kind of story. Really, your resolution is based on what your tip sharpness is, and also how close you are to the sample. I didn't get too much into how it works, but you're lifted up above the surface and kind of going over it, using something called lift mode to keep a constant tip sample separation to do that. So as long as you can stay close to the surface without running into it, if it's not too rough, and you have a sharp tip, then that will help. The only other downside is your signal is probably pretty small because your particles are so small. But I'm happy to discuss it further. You could email me later if you like.
Okay, there was another question. I noticed that STM is one of the function. Is taking DLDV possible?
STM is an option. I bet you guys probably have it on one of the icons. You're wanting to look at density of states and things like that, I think is what that question is. Maybe. I mean, the main thing you're going to have a problem with is you're in air. So you're going to have some absorbed goo on the sample that the tip has to go through to get to the conductive areas. So a lot of work like that is done in ultra high vacuum. So there are people that do ultra high vacuum STM as far as vendors go. Bruker is not one of them. We stuck our head into that a long time ago and went, no, I don't think we want to do that. But I think that answers your question. If not, let me know.
There was just one more question in the chat. Can you talk a bit about imaging hydrogels, ionogels? What's the best mode for that?
Hydrogels, I like to do something that I didn't discuss, of course. So there's a mode called force volume, which is on the icons. It's not on the edge. And it basically does the old-fashioned force curves, but does an image with it. It tends to be slower, and the pixels are usually a little farther apart, so the resolution's not as good, although that has improved lately. On the older instruments, it was kind of a nightmare, but it was possible. The newer instruments, it works quite well. It's called fast force volume. You'll find it on the icons. And I like to use, and the reason I like to use force volume is that you have access to the full Z range of the scanner. So it's 10 micron Z range. On PeakForce mode, the maximum Z range is 600 nanometers. And so what happens is if you press a tip into a hydrogel, which is extremely soft, that means mostly water, then the tip will press in for a while before it starts deflecting upward, even with a super soft cantilever. And so you may use up the whole 600 nanometers and not even have the cantilever deflecting yet. So you may need a couple microns, for instance. So in that case, force volume allows you to have that large access. There's also some tips, which I also didn't talk about, which are intentionally dull. So I don't want to use a 2 nanometer or 5 nanometer tip for something like that. I want to use a tip which is not sharp, because otherwise it'll just slice right through the hydrogel. So we have some we actually developed for live cells. You don't have to use these, but I like them. They're known spring constant. The known tip radius, usually 65 nanometers. And it's really easy to calibrate them. So if a lot of people are interested in modulus on hydrogels, so you can calibrate the deflection without touching the surface, if you're familiar with this. So it's a lot easier once you're in liquid. And then use these tips, which are rather dull with low spring constants, and it worked quite well. So I worked with a number of people that have been doing that. So that's what I tend to use for fast force volume and these dull calibrated probes.
I don't think there were any more questions. Oh,
Yeah, I have.
there you go, Shining. Good. Can you take those questions?
Yeah. I have first a couple questions. General one is, John, you see any trend in the future that is PeakForce tapping mode will replace the conventional contact and the tapping mode?
No, I don't think it'll ever replace them, because they all have their pluses and minuses. You know, I mean, sometimes you do want contact mode. Some of the some modes, like conductive AFM, I think I briefly mentioned, is traditionally contact mode. Tapping mode, the resonant behavior is used in order to look at magnetic fields, electric fields. I mean, a lot of this, honestly, you can get away from those modes if you want to. In fact, I don't do a lot of tapping or contact anymore, just because I don't need it most of the time. But I do still use it. I don't think it'll ever totally replace them, but it is being pretty well adopted. It's a lot of benefits.
Okay, that's great. Thank you. I have a second question. I'm very interested in the deep trench, the trench measurement with this PeakForce. So currently we have the ScanAir probe, handles both contact and PeakForce mode, handles two modes. So is it better to having a special probe if we need to measure the deep trench? Is there any aspect ratio limit if we do that?
Yeah, that's a good question. So it's basically just a geometry problem, right? So if you have a deep trench, but it's super wide, then the tip can probably get down to the bottom of it, and that's fine, and that's better, because if you get into the high aspect ratio probes, then those are special probes that you would have to get. So it just depends, you know. You can go on to the I showed that BrukerAFMprobes.com website. If you go there, it'll tell you what the dimensions of the tip is. So you'll know what the angles are on the left, the right, the front, and the back. And you can, you know, see if it would reach the bottom. You can calculate it out. You could also just look and see if you're just getting a V shape all the time and never seem to get down to the bottom of what you expect, whether it's flat or something else. So if you're not getting to the bottom, then yeah, you need to go to, there's probes that are either machined by focused ion beam. Those are used more for tapping, if you're using tapping. For PeakForce mode, we tend to use ones that are grown on the end. So in that case, you would need to go to those. And they have different links. And, so.
Exactly. Well, thank you so much for explaining the time to prepare the good talk. It's very enriching, helpful. Okay.
Yeah, well, thank you. I enjoyed it. Thanks for asking. And
There's no more questions.
Oh, you got more questions?
I don't think so.